What specific problem does the new method aim to solve?
The new method, alignment via optimal transport, Maths FAOT, aims to solve the problem of aligning large language models, LLMs, with human preferences by introducing a distributional optimization approach for fine-tuning LLMs from human preference data. This method focuses on inducing stochastic dominance of the reward distribution of chosen responses over rejected responses, ensuring that the preference is reflected not only on average, but also distribution ally. Maths FAOT addresses the challenge of ensuring that LLMs follow human preferences, values, ethics, and desired behaviors to reduce the risk of generating harmful, biased, or inappropriate content. By devising a new objective function that encourages dominance of chosen rewards over rejected rewards, Maths FAOT enables distributional alignment in both paired and unpaired settings, providing a novel solution to the critical issue of aligning LLMs with human preferences effectively and accurately.
How does the proposed method work, and can you illustrate it step by step?
The proposed method, alignment via optimal transport, Maths FAOT, works by inducing distributional alignment between chosen and rejected responses in language models, LLMs, based on human preference data. The process involves devising an objective function that enforces first-order stochastic dominance, FSD, of the chosen rewards distribution over the rejected rewards distribution. This alignment is achieved through a convex relaxation approach that minimizes the violation of FSD using a smooth cost function. The method involves solving an optimal transport problem with a convex cost function, where the goal is to ensure that the optimized policy results in the chosen responses dominating the rejected responses across all quantiles. Step by step, the Maths FAOT method involves 1. Defining the reward model R_theta xy, which is a log likelihood ratio between the LLM policy and the reference model. 2. Formulating the optimization problem to minimize the violation of FSD by inducing stochastic dominance of the chosen rewards distribution over the rejected rewards distribution. 3. Casting the optimization problem as a one-dimensional optimal transport problem with a convex cost function h. 4. Solving the optimal transport problem using a sorting algorithm to match quantiles of chosen and rejected rewards. 5. Employing a soft sorting technique such as Sinkhorn algorithm to allow backpropagation during optimization. 6. Adapting the method for unpaired data by defining the reward based on the log likelihood ratio of positive and negative outcomes. 7. Extending the method for paired data by considering the log likelihood ratio of positive to negative outcomes under the policies being optimized. 8. Ensuring the method satisfies assumptions on the OT cost, reward, and policy hypothesis class for statistical analysis. 9. Evaluating the performance of Maths FAOT against other alignment approaches on paired and unpaired datasets using various evaluation metrics and benchmarks. 10. Analyzing the impact of parameters such as batch size and loss function on the performance of Maths FAOT. In summary, Maths FAOT aligns LLMs with human preferences by optimizing the policy to exhibit FSD dominance of chosen rewards over rejected rewards, ensuring distributional alignment and improved model performance.
What are the theoretical or practical benefits of using this method?
The theoretical benefits of using the alignment via optimal transport, Maths FAOT method include the ability to induce distributional alignment through a new objective function that ensures first-order stochastic dominance, FSD, of chosen rewards distribution over rejected rewards distribution. This method allows for a one-dimensional optimal transport problem to be solved efficiently for large language models, LLMs alignment. Additionally, Maths FAOT enjoys nice statistical properties and achieves the parametric rate due to its smooth one-dimensional optimal transport problem objective. The method also provides a way to relax the problem to minimize the violation of FSD, ensuring that the optimal parameter results in the desired dominance. Practically, Maths FAOT has shown state-of-the-art results on the Alpaca leaderboard, outperforming other alignment strategies like direct preference optimization, DPO, Kahneman-Tversky optimization, KTO, and identity policy optimization, IPO. The method does not require iterative training processes and can align LLMs effectively using a convex relaxation approach, making it computationally efficient and suitable for real-world applications. Additionally, Maths FAOT has been shown to be robust to variations in batch size and loss function choices, providing a stable and reliable alignment method for LLMs.
How is the method validated or tested in the paper?
The method in the paper is validated and tested through experiments on a diverse set of base large language models, LLMs, and datasets. The validation includes comparing the proposed alignment via optimal transport, Maths FAOT method with current state-of-the-art alignment approaches such as direct preference optimization, DPO, Kahneman-Tversky optimization, KTO, and identity policy optimization, IPO. The experiments involve using both paired and unpaired datasets, with the paired dataset being the ultrafeedback binarized dataset, and the unpaired datasets being PKU beaver-tails and help steer. The performance of the alignment methods is evaluated using popular metrics like AlpacaVal and OpenLLM benchmark. The AlpacaVal metric uses a GPT-4 model as a judge, and to limit expenses, a Llama 3-70B instruct model is also employed for evaluations. Additionally, the aligned models are tested on 6 key benchmarks from the OpenLLM leaderboard, including AI2 Reasoning Challenge, HelloSwag, MMLU, Truthful QA, Winagrande, and GSM-8K, using zero-shot prompts for a more challenging evaluation setting. The experiments are conducted using a compute setup with 8 H100 GPUs, LoRa for parameter-efficient fine-tuning, and the FSDP setup for training over multiple GPUs. The results of the experiments are presented in tables, showing the performance of Maths FAOT compared to other baselines on various datasets and benchmarks. The impact of batch size, choice of loss function, and beta value on the performance of Maths FAOT is also analyzed and discussed in the paper. Overall, the method is rigorously tested through comprehensive experiments and evaluations on different datasets and benchmarks to demonstrate its effectiveness and superiority over existing alignment approaches.
What results were achieved with this new method?
The new method, alignment via optimal transport, Maths FAOT, achieved significant results in LLM alignment. Specifically, on the AlpacaVal benchmark using GPT-4 as a judge, the Maths FAOT unpaired approach scored 31.3%, showcasing a substantial improvement over the base Merlinite 7B model. This result positioned the Maths FAOT aligned LLM on the AlpacaVal leaderboard ahead of strong competitors like KTO Mistral Pair and other 7B parameter models, even reaching the level of Mixtral -8 by 22 BVO. 1. Additionally, on other LLM benchmarks, Maths FAOT performed competitively with other baselines. The experiments also demonstrated that the performance of Maths FAOT aligning LLMs was impacted by factors such as batch size and the choice of the loss function. The results showed that as the batch size increased, the AlpacaVal score also increased, aligning with the theoretical expectations. Furthermore, the impact of the beta parameter on Maths FAOT performance was analyzed, revealing that higher betas led to decreased alignment performance, prompting the choice of beta equals 0.01 for optimal results. Overall, the ablation results comparing hard and soft sorting, as well as the variance of AlpacaVal scores across multiple runs, demonstrated the robustness and effectiveness of the Maths FAOT method in aligning LLMs.
What are the limitations or drawbacks of the proposed method?
The limitations or drawbacks of the proposed method, alignment via optimal transport, Maths FAOT, include the computational complexity of the optimization problem. The method involves solving a one-dimensional optimal transport problem with a convex cost function, which can be computationally challenging, especially when considering the need to differentiate through the quantile operation. Additionally, the alternating optimization between the parameter theta and solving the inner optimal transport problem with hard sorting may lead to dependencies in theta only through the order statistics level, limiting the backpropagation on theta. This issue can be partially addressed by using soft sorting, but it adds complexity to the optimization process. Another drawback is the sensitivity to hyperparameters, such as the choice of the loss function and the beta parameter, controlling the divergence of the policy from the reference. High beta values can lead to decreased performance in LLM alignment. Furthermore, the method's performance may vary based on the batch size used during training, with larger batch sizes potentially leading to better results but being limited by computational resources.